About a month ago, I wrote a routine to capture the total CPU used by the task control block. Some folks will say TCB time rather than CPU time. I posted a video and a couple of suggestions were made. I'm going to talk about the suggestions in this video. I originally named the routine CPU time until I learned that IBM already had a routine named CPU time, so I renamed it CPU time 2. I did not like the name CPU time 2, but it worked until I could decide on a better name. CPU time 2 needed a save area. It was suggested to remove the save area since it was not being used. Zed CPU-Time was born. It is the same as CPU-Time 2 with the save area and the logic for it removed. It should be a wee bit faster. Zed CPU-Time. Yeah, I like saying Zed CPU-Time. The third version is really interesting. It was written by David Schroeder. It uses hardware-assisted feature to get to CPU time, which should be faster. That routine was named CPUTIME-9. I will reveal why later. How much faster is CPUTIME-9? And how much does the save area logic impact CPU-Time 2? Welcome to another episode of Dinosaur Parkour, Faster, Better Mainframe Programming. When comparing Zed CPU time to CPU time 2, the most important difference is the save area logic. CPU time 2 provides a save area and there is entry logic to save the registers in the save area and link that area to the prior area. The core logic is the same between these two programs, both for asking for CPU usage in microseconds till time used to obtain the information the old way. It makes a program call to an IBM routine that gets the CPU usage and converts it to microseconds. The exit logic in CPU time 2 handles the restoring of the caller registers before returning. Zed CPU time and CPU time 2 are functionally the same, the main difference being the save area logic at the beginning and the end of the routine. CPUTIME-9 was written by David Schroeder. David's version tells time used to use a hardware instruction to get to CPU time. The parameter ECT equals yes means use the extract CPU time instruction. It is an instruction. The value returned is TOD format. TOD stands for time of day clock. The significant thing about the TOD format as far as the time used macro is concerned is that bit 51 represents a microsecond. Thus, bit 51 is the low order bit. Zed CPU time asks for the data to be returned as microseconds and bit 63 is the low order bit. In David's version, the TOD time needs to be converted to microsecond. That is the purpose of those three instructions after the time used macro. The time used placed the TOD value in the field provided by the caller. Load grande moved the value to register 0. Shift right logical grande moved the bit over by 12. Thus, bit 51 in the TOD format is moved into bit 63. Why shift by 12 bit? 63 minus 51 equals 12. Store grande stores the updated register 0 value back in the double word provided by the calling program. Was any significant value lost while doing the shift right? That is something else I want to test in this video. This is the main line of the test program. I commented out line 36. When we look at the numbers, I will explain why 36 should be done. We want to test three programs, Zed CPU time, CPU time 2, and CPU time 9. Each test is going to be repeated 3 times. This shows how Zed CPU time is configured. Get the current CPU usage before starting the test. The program is getting the CPU usage twice. once with Zed CPUTIME and again with CPUTIME-9. In the Get CPU paragraph, the same thing is done, but in reverse order. The starting CPU paragraph called Zed, then 9, the ending CPU paragraph called 9, then Zed. Look at how we're testing Zed CPUTIME on line 57 again. Get the starting CPU using Zed routine and David's routine. Line 58 through 60 is a loop that calls Zed CPUTIME 1,000,000 times. Get the ending CPU usage. Perform the paragraph that calculates the differences and shows the results. Line 116 to 120 uses the start and end CPU values obtained by CPUTIME-9 to compute the CPU calling Zed CPUTIME 1,000,000 times. Lines 122 to 125 calculate the same thing using the start and end values from Zed CPUTIME. Look at the display line. The ending CPU is shown, the starting CPU is shown, followed by the difference between the end and the start. End minus start equals CPUTIME used. The purpose of displaying these values for both Zed CPUTIME and CPUTIME-9 is to see if there was any significant loss of value when the shift right by 12 bits were done. The paragraphs to test CPUTIME-9 and 2 are configured the same way as this measure Zed CPU paragraph, the only difference being the name of the program on line 59. Look at the end time. The end time is the same for both Zed CPUTIME and CPUTIME-9 for every pair of values except the last one, which have a 1 microsecond difference. Focus on the start time. Let's ignore the first pair of values for now. The rest match except for the last pair, which are 1 microsecond apart. It looks like CPUTIME-9 is spot on. The shift right by 12 bits does not impact the desired result of the routine. Time to talk about the first pair of starting numbers, 70 microseconds of difference. Why is the first pair value between Zed CPU and CPUTIME-9 more than 1 microsecond off? The first thing that the program does is get the starting CPU time. The get starting CPU paragraph calls Zed CPU time first, then David's routine. Zed CPU time tells time used to get to Eustace the old way. The time used macro does a small bit of setup work and then uses the program call instruction to invoke an IBM routine. I think it took 70 microseconds for this routine to load and initialize itself, which is why there's a big hit on the first call, which is why you should make one call to the Get CPU usage routine before taking any measurement. That is why line 36 in the main line should not be commented out. Call the Get CPU usage routine once before taking any measurement to force any setup variances out of the way. We were curious as to how much overhead does the SaveArea logic add. We have to ignore the first pair of numbers because the variance is caused by the setup done on the first call to the routine. Looking at the CPU used between Zed CPUTIME and CPUTIME-2, it appears that the SaveArea logic adds about 3,000 microseconds of overhead for 1,000,000 calls. Not enough to worry about. Now it is time to compare Zed CPUTIME to David's routine. Yeah, David's routine is blazingly faster. The extract CPUTIME instruction is way faster than the old way, which makes a call to a routine. Granted, this difference is spread across 1,000,000 calls, but that is a significant difference. The extract CPUTIME instruction was introduced on the Z9 hardware. That is why I named the routine CPUTIME-9. David's code only works on Z series machines. I ran this test on Z14. If your chop stays on supported hardware, it is worth the effort to see if David's code worked. If you're on older hardware, Zed CPUTIME worked just fine, even though these numbers may look really slow. Making a single start and end call to Zed CPUTIME adds very little overhead to a measurement test that repeats something thousands or millions of times. We're talking about nanoseconds of impact to make a start and end call. David's routine, if you can use it, makes less of an impact. It is faster.